Okay, where are we? We're in part 4. So far we know where it started, we know what happens after 10 years, and we know where it's going to end, in theory. Who knows why they suddenly magically stop decreasing after 150, but whatever. Here's the way they've set it out. Now, I want to say two things. Number one, you didn't have to solve this as an inequality. You can see why they've solved it as an inequality though, right? Like, look at the language of the question. It says when the population falls below 200. So therefore, any value less than 200, that's fine. Of course, they actually want a specific point in time. So there's nothing wrong with doing something like this, right? Instead of solving for p is less than 200, just solve for when p is 200. I wouldn't be surprised if most of you did this. One of the reasons why that's advantageous is because equations, much less messy than inequalities. You don't have to worry about a direction of the inequality and so on. But then, of course, what you've got to do from that is once you find that value, right, where that's satisfied, then you have to interpret that result accordingly. So you have to make a statement, right? Your last line can't be t equals 35.83 because that's not, like, there's more than that to the question, right? So that's the first thing I want to say. If you set it up as an equation rather than as an inequality, then you've got to do that. Secondly, we've actually said this, and here are the 2 marks, by the way. There's not really anything for these initial lines, like they're very easy to get. Your 2 marks are for, manipulating to make t the subject, so you've got your exponential and your log there. And then your second final mark was to actually find out what that time was. So, I'm going to get to that. So, when I say 1 mark is on stating the time, okay? Here, if you ended on t is greater than 35.83, then you've answered the question, okay? But if you ended on t equals 35.83, you have not, right? Because when the population falls below 200, there's a whole range of times when the population has fallen below 200, right? Okay, now, again, there's no accuracy provided on the question, I don't believe, so I'm not going to worry about rounding at the moment. In this case, you got lucky because the normal way of rounding is going to be the correct way of rounding in this case. You've got to round up because if you went down, suppose it was 35.2 years and you went down to 35 years, which is the nearest number, what will the population be? Well, it'll be more than 200 at that point, right? It still hasn't dipped down. Luckily for you here, it didn't matter because whichever way you approximated would have been fine. But the thing I actually wanted to make note of was this. I kind of skipped over it. When you translate from this exponential equation, right, down to this equation, which is a log equation, okay, we can kind of do this by definition, yeah? Like, for example, if I said to you 2 cubed equals 8, then you could write the log equation off of this, instead of the exponential equation, as log base 2 of... log base 2 of, 8 equals 3, right? Now, the thing with that is that it's an equation, so you can write the 3 on the left, so you can write the 3 on the right. Doesn't matter. But the way this has been set up, it's an inequality, so it does matter. But taking logs of both sides sort of rescues you from this problem. Because think about what this, this top line, let me put it in a new color for you. Think about what this top line means. This means you've got a number on the left, and it's smaller than the number on the right. Yeah? So if you take logs of both sides, the log of a small number will be smaller than the log of the big number. Remember what logs are? Well, back when we introduced this, right? Logs are an amount of time to grow to a certain amount, a certain size, right? I'll be able to grow to a smaller size faster, right? It's a smaller amount of time versus a big amount, right? So if you take logs of both sides, rather than jumping straight to, I can interpret this as a log equation, you'll preserve the direction of the inequality, okay? So, that was the first question. Any queries?
So if you had an equal sign, it's okay as long as you have a final statement?
Yep. Yeah, that's right. If you have this thing here, that kind of says, I understand what this equal sign means. I understand that solving that, just like if you were solving, if you're solving something like this, right? Right? You're solving something like that, and there's nothing wrong with saying, okay, I want to find the boundary point, and I'll do that by solving the equation that gives me the boundary point. And then you're going to have to obviously answer with an inequality, because you've got to return back to the original question. And it's exactly the same deal with this exponential growth and decay. Okay? Cool. Let's move on to number 2, which I think was decidedly more straightforward, so I'm just going to go ahead and tell you where the marks are. Part 1, that's the case you've seen many, many times, so all you have to do is differentiate. Hope you all got that. Part 2, there are 3 marks. And that's because there are three things you needed to evaluate. You had to find A to find K. Then you had to find K to find M.
Wait,
And then you found M.
for K, can you just leave it in that long?
Okay, so yeah, absolutely.
Oh,
Absolutely.
okay, so-
Yeah.
Oh god.
Wait, what did you say? What?
Don't I always leave it exact?
Yeah.
I don't think I ever approximate.
M0
Wait, what?
10.
Oh, you did something. Oh, okay. Yeah, I see what you did. All right. Rookie error. All right. At least you got 2 out of 3 on that, probably. So can I say I've said this many times under exponential growth and decay, and each of he's talking about what happens. Sorry, he's talking about what happens down here. The thing about rates of change and exponential growth and decay is that the differentiation and even the integration where it's required is not difficult. It's the exact opposite for the extension 2 students of extension 2 integration, where it's like, here's the hardest integral you could possibly have. This, all the calculus is easy. What's hard is arranging them, interpreting them, actually giving you the right equation so you get the answer out and get a value that's correct. Okay? So A, K, and M, there are your 3 marks. That was a simple one. So turn over. We'll look at question 3 now. No marks, but bonus points if you drew that tank with water coming out of it, like I always do. Here we go, part 2. This is the first time there's 2 marks, so I'll just explain where the marks go. Just like before in question 1, you're given a volume expression as a function of time, but you don't have a derivative. So if you want to rate, you have to find the derivative. So that's the first mark, differentiate. Right? The second mark is then just to say, well, at time 20, at t equals 20, tell me what the rate of change is. So it's draining 80 liters per minute, or negative 80s, okay, but I keep on saying, don't skip, guys. Don't skip on the sentence.
So sorry, what was the answer to rate out of?
Oh, sure. 2,500 liters. Okay, now, part 3 was interesting. It was probably surprisingly interesting. And there are a few ways to go about this, but I think this is probably the most efficient way. The question says, at what time does the model predict that the water will drain from the tank at its fastest rate? Now, when you hear that word fastest, you should be thinking, oh, this is a maximization problem, right? What am I trying to maximize?
That's why the answer is only 1 mark.
I'm trying to maximize dv on dt, right? So if you want to maximize the derivative, you've got to climb 1 level of differentiation down. So that's why they've gone to the second derivative. It's an easy function to differentiate. Just go for it. You get a constant? So what does that mean?
It's always increasing.
It means it's always increasing, going from a really negative number, progressively going out to 0. Wait, of course it should, right? Because it starts draining out really fast, and as it ekes down to the bottom, it slows down, right? Air pressure and all that kind of thing. So therefore, though, for 2 marks, you can't just know that. You can't just know, oh, it's going to be fastest at the beginning, okay? You've got to justify. There are no stationary points here. You do that by finding the second derivative, right? On the basis of that, that means that the maximum flow rate has to happen at an endpoint, right? Time equals 0, time equals 60. It's got to be one of those. So you just test them. Right?
I wrote this and then put a graph on it, and it's...
I'll look at your individual solution later. I'm happy to look at people's individual solutions afterwards. Yeah, question.
I graphed the gradient function.
Yeah.
Okay, so if you have a graphical solution, all good with a graphical solution, with one condition, your graph has to be good. It has to be good enough to argue off, right? So if your graph is like some rough, those are not rough things. If you're doing something rough and you're like, oh, it roughly looks like that, it's not sufficient. If you want to make a graphical argument, your graph has to be really good. I think this is kind of quicker, but anyhow, the graph is fine. So they want the fastest, so that's why it's minus 120, and that's times 0. Okay, last question. Now, remember I said that this was done very poorly. Okay, you can see some stats over there on the right-hand side. What's going
Oh
on?
my god.
Some people, many people actually, thought, oh, it's a flow rate. Better differentiate, right? But of course you don't have to, because this is the opposite of those earlier questions where you get given a volume expression. Here you're already given the derivative. That's what that 2 plus t squared on t plus 1 is, right? So all you needed to do was take the difference. Now, just quickly, right? This is a part 1. They didn't say hence or otherwise in part 2. But when there's a part 1, 2, 3, it's always implied. That's why it's a part 1, 2, 3. So when you look at this thing and you're like, I don't want to integrate that. Yeah, you don't have to integrate that. Because in part 1, you showed that the difference was t.
Yeah, I thought.
So use that and then it becomes quite trivial.